So in this lesson, we're going to be talking about partial fraction decomposition. And the best way for me to explain what partial fraction decomposition is for us to take a stroll back to lesson 4, where we looked at examples where we added and subtracted rational functions. So all I mean by that is we looked at examples like this, where you had to find a common denominator and add these things together. So let's jump back into this example, which hopefully is a refresher because we did do problems like this back from lesson 4. If you need to pop back to lesson 4 to refresh your memory, please do that. So in order to add fractions, we need to have a common denominator. Our common denominator will be the product of these two denominators. So I'm first just going to set this up. We had 5 over x plus 6 in the first fraction and 4 over 3x plus 1 in the second fraction. I need to get that common denominator in there, so the first fraction needs a 3x plus 1 in the denominator, which means I'll also need to put it in the numerator, and the second fraction needs the x plus 6 in the denominator, which means I'll also need to put that in the numerator. So now I'm just going to be doing some distributing. I'll distribute the 5 to these two terms here to give me 15x plus 5, and that's still all over x plus 6 times 3x plus 1. And then in the second fraction, I will distribute the 4 to give me 4x plus 24, and that's still over the same denominator. I'm just going to switch the order that I'm writing them so they actually look like they're the same, because we know it doesn't matter what order we multiply in. And so now that we have a common denominator, I can write this as one big fraction. I could have done this a while ago, but I think it's a little bit easier to see it like this. Now I'm actually going to combine and add these two fractions together. So I have a 15x plus 5 plus 4x plus 24. And now I need to combine like terms. So I end up with 19x from the 15x and the 4x plus 29. And all that is over x plus 6 times 3x plus 1. Okay, so if we were in lesson 4 and we were told to add those two functions, this would have been our answer, and then we would have been done. So what we're going to be doing in this lesson is we're going to be starting with an expression that looks like that and working our way backwards to write it as a sum of partial fractions. We're going to be decomposing these. Decompose means break down. We're going to be breaking down these expressions into partial fractions. So let's take a look at how we would do that. I'm actually going to work with this exact same example and work backwards to show you how we get that. So if I know, so starting here, right, this is the answer that we just got. Starting here, I can see those two factors in the denominator, the x plus 6 and the 3x plus 1. Well, those have to be the denominators of my partial fractions. So because I had two sets of factors in the denominator, I set up two fractions. What we really need is to know what a and b are. What we really need is to know what those numbers are in the numerator, and then we would be done. So from this setup, I am going to clear out all of the fractions. That's the next thing we're going to do. We're going to clear out all of the fractions. And how we do that is we're going to multiply both sides of that equation by the common denominator. So we're going to multiply the left side of the equation, the 19x plus 29 over x plus 6 times 3x plus 1. First, let me just write the equation. A over x plus 6 plus b over 3x plus 1. Okay, so everything in this equation is getting multiplied by the common denominator. So notice that that is 3 terms. So I am multiplying this term by the x plus 6 times the 3x plus 1. I am multiplying this term by the x plus 6 by 3x plus 1. And I am multiplying this term by x plus 6 by 3x plus 1. Okay, so when we do that, this cancels, that cancels, that cancels, and we're only left with 19x plus 29 on the left side of the equation. When we go to the fraction that has the a in the numerator, the x plus 6 will cancel, but the 3x plus 1 does not cancel. So we would have a times parentheses 3x plus 1 When we go on to that last fraction, the 3x plus 1 will cancel, but the x plus 6 does not cancel. So then we have a b times an x plus 6. Okay, so now I'm going to simplify and I'm going to combine like terms. There's not much for me to simplify on the left side of the equation. I'm just going to leave that as 19x plus 29. But on the right side of the equation, I need to distribute the a to both of these terms in here, and then I'll also distribute the b. So when I distribute the a, we get 3ax plus a. 3ax plus a. And then I'm going to distribute the b, so I'll get a plus bx plus 6b. Now I'm just going to move some terms around. I have 19x plus 29. I want to put my x terms together on the right side of the equation, so I have a 3ax, and I'm going to move the bx term to be next to that, and then all the terms that don't have x, like the a and the 6b, I'm going to write at the end. So plus a plus 6b. And the reason that I put my x terms together is because I want to combine those terms by pulling that x out. So both of these terms right here had an x. I'm going to pull that x out right there, and let's see what we're left with. Well, the first term left us with a 3a, because we had 3ax, but we pulled the x out. And the second term just leaves us with a b, because we had bx, but we pulled the x out. And then we still have the plus a plus 6b. Okay, so we have that all simplified with our terms combined. The next step tells us that two polynomials are equal if and only if the coefficients on like terms are equal. So what does that mean? We are saying that the left side of this equation is equal to the right side of the equation because we have an equal sign in between them. But the only way that all of this can be equal to all of that is if the number in front of x on the left side of the equation is equal to the number in front of x on the right side of the equation. So it must be true, that's why we pulled that x out, by the way. That pink x is why we pulled that out. So it must be true that 19 is equal to 3a plus b. And what must also be true is that the number that has no variable on the left side of the equation must be equal to the number that has no variable on the right side of the equation. So this is called equating coefficients. This has to be equal to that if both sides of the equation are equal. So it must also be true, I'm going to write this right under it, that 29 is equal to a plus 6b. Now this is a system of linear equations. Just like what we looked at in the previous lesson where we were solving systems of linear equations using we didn't call it elimination, using substitution and the addition method, that's the same thing that we have right here. I'm going to solve this system using, let's do the substitution method, okay? Because I'm going to do substitution because this second equation, I can quickly solve it for a by just subtracting 6b from both sides to see that a is equal to 29 minus 6b, and then I'm going to substitute that in to the first equation. So in the first equation, we had 19 equals 3a plus b. I'm going to replace the a with 29 minus 6b. That was me doing the substitution. Let's continue to simplify this. I'm going to distribute the 3. 3 times 29 is 87. That looks like a 68. It's not. It's a 6b. Okay, so now distribute the 3. I'll have a negative 18b. I don't know what color pen I'm using. This is why I just use black. Okay, so I have 19 equals 87 minus 18b plus b. Let's continue to combine like terms. The negative 18b and the positive b will come together to give me a negative 17b. So I have 19 equals 87 minus 17b. I'm going to subtract 87 from both sides. I'll just rewrite this equation so you can see where I'm subtracting the 87. So 19 minus 87 is a negative 68. So we have a negative 68 equals negative 17b, and then we will divide both sides of the equation by negative 17 to get the b by itself. And we get that b is equal to a positive 4. So now that I know that b is equal to a positive 4, I can just take this value of b and plug it into this equation, which was a is 29 minus 6b. I know b is 4, so a is 29 minus 6 times 4. So a is 29 minus 24, a is 25. A is 5. So we found that b is 4 and a is 5. So how we finished the whole partial fraction decomposition is, well, we already had it set up like this from the start. We already knew that the partial fraction decomposition had to look like something over x plus 6 plus something over 3x plus 1, and we just found those somethings. So now I'm just going to fill in what a and b are into that form. So a is 5, that is 5 over x plus 6, plus b is 4 over 3x plus 1. And that is our answer for the partial fraction decomposition. And notice that's exactly what we started with up here. 5 over x plus 6 plus 4 over 3x plus 1. So one of the things that we're going to spend some time talking about, you'll notice that the objective for this is not just to decompose into partial fractions. That's what we did. But it's impossible to decompose into partial fractions if you don't know how to set up the partial fraction. And what I mean by that is this is the setup part, right? We have to be able to get that right before we can go in and start finding these letters. So one of the next things we're going to talk about in this lesson is how do we use what we see in this denominator to let us know how to set up the partial fractions before we go in and start doing all this crazy algebra to find these coefficients. Before I stop this video, if you're going to be doing partial fraction decomposition, you need to make sure that the degree, all degree means is highest exponent, that the degree of the numerator is less than the degree of the denominator. We should not be doing partial fraction decomp if the numerator has a higher degree. And in order to do partial fraction decomp, the denominator needs to be completely factored. We have not yet talked about factoring much in this course, and so you will be given denominators that are factored for the most part. You might have to pull out like an X or something like that, but for the most part, you won't have to do any crazy factoring to do your partial frac decomp, at least not for now, not until after we talk about factoring. The next thing is we will only be looking at examples where the factors in the denominator are linear or repeated linear factors. And so what I mean by that is that this factor is a line. This factor is a line. We're not going to be doing things that say like x squared plus 6 in the bottom, because then that changes the setup of what we're going to be doing. So we're going to look at kind of like the simplest examples of partial fraction decomposition in this lesson.